Hello everyone and welcome to this in-depth analysis of a major seismic event currently shaking the California coast. For several days now, the Los Angeles area has been experiencing what seismologists call an earthquake swarm. This is a series of earthquakes occurring close together in both time and space, without a single main event being clearly identifiable. In this video, we will break down together the official data from the United States Geological Survey, also known as the USGS. We will explore the geological context of this region, learn how to interpret seismogram, and most importantly, discuss what science tells us about the risks ahead. So get comfortable because we are about to dive deep into the world of plate tectonics. To understand this earthquake swarm, we first need to understand why California is one of the most seismically active regions in the world. California sits on the boundary between two major tectonic plates. On the west side, we have the Pacific Plate, and on the east side, we have the North American plates. These two geological giants are moving relative to each other at a speed of approximately 46 millimeters per year. That is roughly 1.8 inches annually. This creates what geologists call a transform or slip boundary. Los Angeles is literally built on top of complex network of active faults. The most famous one is, of course, the San Andreas Fault. It stretched for about 1,200 kilometers, or roughly 750 miles, throughout California. But San Andreas is not only treats. Let me talk with you about the main fault in the Los Angeles area. First, we have the Newport Inglewood Fault, stretching about 75 kilometers. Then there is the Punt Hillstrasse Fault, roughly 40 kilometers long. We also have the Raymond Fault at 22 kilometers, the Hollywood Fault at 15 kilometers, and the Santa Monica Fault at 45 kilometers. The hidden or blend faults like Puentes Hills are particularly dangerous because they pass directly under the downtown. Los Angeles without reaching the surface. This means they are harder to study and can produce earthquakes with little warning. Okay, before we analyze the data, let's clarify what an earthquake swarm actually is. Unlike a classic main shock plus aftershock sequence, an earthquake swarm is characterized by several key features. First, there is now clearly dominant main earthquake. Second, The magnitudes are relatively similar between events. Third, all the earthquakes are concentrated in a restricted geographic area. And fourth, the duration can vary from a few days to several months. Swarms can be caused by various factors. These include fluid movements underground, such as water, magma, or gas. They can also result from adjustment in tectonic stress or even from human activities like fluid injection. Now let's look at the official data from the United States Geological Survey. The observation period began in mid-January. In mid-January 2026, the affected zone covers the greater Los Angeles metropolitan area, centered around coordinate 34 degrees north latitude and 118.2 degrees west longitude. It is how the earthquakes break down by magnitude. Earthquakes below magnitude 2.0 are classified as micro-earthquakes. They are not felt by people, and there have been numerous events in this category. Earthquakes between magnitude 2.0 and 3.0 number in the dozens. These are typically not felt or only slightly felt. Earthquakes between magnitude 3.0 and 4.0 have occurred several times, like this one in Dayo. These are felt by people and can cause minor shaking. Earthquake between magnitude 4.0 and 5.0 represents moderate events. They may occur during the swarm. Earthquakes above magnitude 5.0 require careful monitoring. The focal depths generally range between 5 and 15 kilometers, which is about 3 to 9 miles. This is typical for this region. Let me explain how to read a seismogram. A seismogram is a recording of ground motion caused by an earthquake. When an earthquake occurs, it generates three main types of waves. The first type is called P wave, which stands for primary waves. These are the fastest waves and arrive first at seismic station. They are compression waves that travel at approximately 6 kilometers per second through the Earth's crust. That is about 3.7 miles per second. The second type is S waves or secondary waves. These are slower but more destructive. They cause shearing motion perpendicular to their direction of travel. They travel at roughly 3.5 kilometers per second. The third type is surface waves. These are the slowest but often the most damaging. They travel along the Earth's surfaces and cause the rolling motion that people feel during earthquakes. The time difference between the arrival of P waves and S waves allows seismologists to calculate the distance to the earthquake's epicenter. By using measurements from multiple stations, they can triangulate the exact location. Seismologists use something called focal mechanism to understand how a fault moved during an earthquakes. These diagrams are often called beach balls because of their appearance. They show us the orientation of the faults, the type of movement, whether normal, reverse, or strike slip, and the direction of slip. For the core and swarm, the mechanism suggests predominantly strike slips motion, which is consistent with the known faults in the region. Looking at the spatial distribution of the earthquakes in the swarm, we can observe several patterns. The earthquakes are concentrated between 5 and 12 kilometers in depth, that is roughly 3 to 7.5 miles below the surface. There is a linear alignment suggesting an underlying fault structure, and there appear to be possible migration of activity over time. These characteristics are typical of a progressive stress release along a fault segment. Okay, before we discuss prediction, I need to make something absolutely clear. Short-term earthquakes prediction, meaning prediction, the exact date, time, and location remains impossible with current technology. The probabilities I will present are statistical estimates based on historical data and model. They are not prediction. No one can predict an earthquake with certainty. The USGS uses a model called ETAS, which stands for Epidemic Type Aftershock Sequence, to calculate the probability of aftershocks following an earthquake or during a swarm. This model takes into account three main factors. These models take into account three main factors. First, the magnitude of previous events. Second, the time elapsed since the last earthquake. And the third, the statistical characteristic of the region. Okay, for the probabilities for Los Angeles, based on typical usage modeling, here are hypothetical probability estimates for the region. For the next 7 days after significant swarm activity, the probability of an earthquake magnitude 3.0 or greater is between 70 and 90%. The probability of an earthquake magnitude 4.0 or greater is between 15 and 30%. The probability of an earthquake magnitude 5.0 or greater is between 2 and 5%. For the next 30 days, the probability of an earthquake magnitude 5.0 or greater is between 5 and 10%. The probability of an earthquake magnitude 6.0 or greater is between 1 and 3%. Then these probabilities will decrease with time if the activity calms down. Okay, for the famous big one is not a myth. The USGS estimates there is a greater than 60% probability that an earthquake of magnitude 6.7 or greater will strike Southern California in the next 30 years, or an earthquake of magnitude 7.0 or greater on the San Andreas Fault The probability is approximately 75% over that same period. Let me put this in historical perspective. In 1857, a magnitude 7.9 earthquake struck Fort Tijan. In 1906, the famous San Francisco earthquakes measured magnitude 7.9. In 1933, Long Beach experienced a magnitude 6.4 earthquake.